And so future iterations are all carried out in the same way as we saw for iterations 1 and 2. And if we graph the power levels and signal to interference ratios over time, we get graphs that are shown over here. And in the green, we've shown link 1, in the red, link 2, and in the blue, link 3. So a couple comments about this. First of all, we can see the patterns of overshooting and undershooting here continue for a few more iterations. So for instance, we trace out link 1, drops down, goes up, drops down, goes up, drops down, and eventually they settle down, and they settle down at the same time for each of these transmitters. And so once we converge, we say that we have reached the equilibrium, and that's the definition of convergence of this algorithm, is that it'll stop updating over time, and we will have reached this state of equilibrium. And so that happens after, maybe about 10 iterations here. So 10 iterations and beyond, nothing's changing anymore. And again, we've converged. And so the convergent SIR levels are 1.8, 2.0, and 2.2, as was necessary. And these levels down in here are 1.26 for the power levels milliwatts, 1.31 milliwatts, and up here for link 3 has about 1.99 milliwatts. And so the question here is, why is link 3's power level so much higher than the other two? Well, it turns out that link 3 actually has a few things working against him, if you remember. First of all, it has the highest noise component. So that's going to affect its SIR. And there's no way to really overcome that because the noise won't change over time. So that's why, again, he needs to have a higher power level than everyone else to compensate for that fact. Second is that he actually has the highest interfering channel gains. Interfering gains. So if you remember, they were both 0.2, whereas each of the other ones had 0.1 and 0.2 coupling into them. Link 3 had 0.2 and 0.2 from links 1 and 2. And that makes a difference, so the channel conditions are worse, and there's more actual interference going on to this link than the other two. And the third is that it's actually asking for a higher SIR. So with all that in mind, it makes sense that link 2 would have the highest power level out of all of them, because it needs to have a higher power level in order to overcome these three obstacles. And so now, just to make a few comments about DPC in practice. First of all, we said before that it's a completely distributed algorithm, and by distributed we mean that it's not centralized. Distributed and centralized are the opposite, and it allows each user basically to make independent decisions driven by their own needs. So each of these links, again, all they need to know is they need to know the measured SIRs, the ratio of the measured to the desired, or the desired over the measured, and that's something that the tower will tell them. So the tower tells each of these links that ratio, and then they just take that and they can multiply it by their current power level, and that's all they need to keep updating their power level. So they don't need to talk to any of the other devices at all. All they need to know is this ratio, and then they just need to cooperate with that ratio when they're updating their current levels. And eventually the entire system will reach its own equilibrium. And we will see also throughout this material, we'll see other algorithms that are actually more centralized, but this is not one of them. This is completely distributed in nature. And so if we looked at this in a real cell, we're going to have thousands of phones, and so in the example that we looked at here, we only had 3 links as opposed to thousands, and so DPC is actually something that's probably implemented about 1,500 times per second. So that's how fast your phone can go through and carry out these computations, because it's again highlighting the fact that it's a very simple and elegant algorithm. It's very distributed, simple, and elegant, which is really important to make us be able to handle this computational requirement of 1,500 times per second. And that's especially true because we have users going into and coming out of the cells. So in our given cell, if we have people moving out, or we have and then we have other people coming in, that's going to change the channel conditions for everyone. And so we need to sort of change these power levels over time.